Welcome to Organic Chemistry. This video will focus on our first functional group set of reactions with alkenes. Let's get started. Alkenes have a carbon-carbon double bond made up of a sigma bond, that's lower in energy, and a pi bond, that's higher in energy. The sigma bond is, of course, stronger, having no angular nodes, around 335 kilojoules per mole, while the pi bond is weaker, around 272 kilojoules per mole. Because that pi bond is higher in energy, because it has that angular node, it's much more reactive. Alkenes use those pi electrons when acting as nucleophiles. We also know that substitution affects stability. A more substituted double bond is more stable, partly due to hyperconjugation, the overlap between nearby sigma bonds and that pi system, which spreads the electron density a bit like resonance. That's why more substituted alkenes are generally lower in energy. So, why are certain alkenes more stable than others? There are two big competing effects: steric repulsions and hyperconjugation. On the top row, we're looking at sterics. When we hydrogenate two different alkenes, notice the heat release, the enthalpy of hydrogenation, isn't always the same. More exothermic means the starting alkene was less stable. Less exothermic means the starting alkene was more stable. Here, adding H2 to a more substituted alkene releases 27 kilocalories instead of 29 kilocalories per mole. That means the substituted alkene was already more stable. Why? Look at the cartoon with the orange circles. The steric crowding between bulky substituents raises their energy. If substituents are arranged with less steric repulsion, the alkene is more stable. While on the right, the energy diagram shows steric interaction between the methyl groups at different torsional angles. The steric bump is worth around 2 kilocalories per mole. So steric hindrance absolutely destabilizes the alkene. Now let's compare that to hyperconjugation on the lower row. When hydrogenation releases 30 kilocalories per mole versus 27 kilocalories per mole, it shows that the less substituted alkene is less stable. Why? Because hyperconjugation stabilizes substituted alkenes. What's happening is that the sigma bonds adjacent to the double bond, those CH and CC bonds, overlap with the pi orbital. That delocalization spreads out electron density just like resonance would. So more substituted alkenes have more adjacent sigma bonds available for hyperconjugation, which makes the pi bond more stable. And the energy difference can be a few kilocalories per mole. For example, 1-butene is about 3 kilocalories per mole less stable than trans-2-butene because trans-2-butene gets the maximum hyperconjugation with minimal sterics. When naming alkenes, we apply the Cahn Ingold Prelog rules to assign priorities to atoms. Compare atoms directly attached to each double bonded carbon. Higher atomic number means higher priority. If they're the same, move outward until you find the difference. If the two higher priority groups are on the same side, we allocate the designation Z for zusammen, which means together. If they're on opposite sides, E for entgegen, meaning opposite. If the substituents happen to be the same, it's possible to use cis-trans nomenclature. However, it is also important to note that the Cahn-Ingold Prelog rules is the more proper naming convention, and every cis-trans isomer can be also named according to the EZ designation as well. Now we move on to alkene reactivity. The most common reaction is electrophilic addition. HCl and HBr add across the double bond according to the Markovnikov rule. The hydrogen goes to the carbon with more hydrogens, and the halogen goes to the more substituted carbon. Why? Because the reaction proceeds through a carbocation, and the more substituted carbocation is more stable. By the Hammond postulate, a more stable carbocation means a lower energy transition state, and so that pathway is faster. The key points for this reaction is that the reaction is regiospecific. That is, it follows Markovnikov's rule. It allows rearrangements via hydride or alkyl shifts, and also that it's not stereospecific. That is, both syn and anti-additions are possible. When the alkene reacts with HBr or HCl, the pi bond first attacks the proton. That gives us a carbocation intermediate. This carbocation is planar, sp2 hybridized. Since it's flat, the bromide ion can attack from either side, from above or from below. Each option is equally probable. Because bromide can attack from both faces, we don't just get syn addition or just anti-addition. We get a mixture of products, some where the substituents add on the same side, syn, and others where they add on opposite sides, anti. This is very different from halogenation, where a halonium ion, as we will see, locks the stereochemistry into anti-addition. Carbocations don't just sit still. They can rearrange into a more stable carbocation. To do this, they can do a hydride shift or an alkyl shift. A hydride shift is when a hydrogen atom next to the carbocation can move with both of its bonding electrons into the empty p orbital. This is equivalent to the hydrogen carrying a quote-unquote hydride anion. The result is that the positive charge moves over one carbon, often producing a more substituted and a more stable carbocation. Hydride shifts are generally easier and more common than alkyl shifts because moving a small hydrogen atom is less sterically demanding. The other, alkyl shifts, occur if no suitable hydrogens are available. And then, only then, can an alkyl group possibly migrate instead. The entire R group moves with its bonding electrons, shifting the positive charge onto a different carbon. Again, this is less common than hydride shifts, but still important when no hydrogens are positioned to stabilize the carbocation. Note how halogenation is distinctly different. Br2 or Cl2 can add across the double bond. But instead of a carbocation, what you form is a halonium ion intermediate. And this halonium ion intermediate prevents rearrangements. What follows is a backside attack from the anion that was produced, and it forces anti-addition. So only trans products can form. Therefore, halogenation is most definitely regiospecific, because the halogen prefers the more substituted carbon. No arrangements are possible because of the halonium ion intermediate, and it is stereospecific. That is, only anti-addition occurs. If you run halogenation in either water or alcohol, you get a halohydrin. One side adds halogen, and the other adds either an alcohol or an ether group. The mechanism is similar. There is a halonium ion formation, and then a nucleophilic attack. The alcohol goes to the more substituted carbon because it's more stable for the transition state. Therefore, this reaction is most definitely regiospecific. That is, it follows Markovnikov's rule for alcohol or ethers. It is not associated with rearrangements because of that halonium ion that's formed, and it is most definitely stereospecific and occurs by anti-addition. Adding water or an alcohol directly to an alkene in order to generate an alcohol or an ether is too slow on its own to be observed. But in the presence of an acid catalyst, a strong acid, hydration will most definitely occur. The mechanism goes like this. The protonation of the alkene occurs first, and we generate a carbocation intermediate. It is then followed with either water or an alcohol attacking, and then we deprotonate that water or alcohol in order to regenerate the acid catalyst. Because it goes through a carbocation intermediate, rearrangements are most definitely possible. Thus, the reaction is regiospecific, that is, it follows Markovnikov's rule. It allows rearrangements, but it is not stereospecific. That is, we will definitely have a mixture of syn and anti-addition products. Oxymercuration is an alternative hydration method. Instead of generating a carbocation intermediate, we form a mercurium ion, which prevents rearrangements just like the halonium ion did. Water then attacks the more substituted carbon, giving a Markovnikov product. In the second step, sodium borohydride replaces the mercury with hydrogen. The key takeaways of this are that it is regiospecific, follows Markovnikov's rule, no rearrangements occur, and it is not stereospecific because the rotation that occurs between steps 1 and 2 that's possible about the sigma bond breaks stereochemical control. In the mechanism associated with hydroboration, we have the opposite of oxymercuration. Here, borane adds across the double bond in a concerted syn mechanism, with hydrogen going to the more substituted carbon and boron to the less substituted one. Notice how this contrasts to what we saw earlier with halogenation. Indeed, in that case, the halogens were more electronegative than hydrogen. And in this case, however, hydrogen is more electronegative than boron. So in this case, we have anti-Markovnikov addition because of that. And therefore, it's regiospecific in an anti-Markovnikov manner. Because it's a concerted syn mechanism, there are no rearrangements, and it is stereospecific. That is, it adds on the same side, syn addition. To remove boron and replace it with a hydroxyl group, oxidation occurs using peroxide in hydroxide to form hydroperoxide. Notice how the boron is replaced with the hydroxyl group through a series of steps. And the net result, again, is that this mechanism is regiospecific, anti-Markovnikov. It occurs through no rearrangements, and again, syn addition. This is the preferred way to make anti-Markovnikov alcohols. Finally, we come to catalytic hydrogenation. In the presence of a metal catalyst like platinum, palladium, carbon, or nickel, rainy nickel, hydrogen adds across the double bond. Because both hydrogens come from the catalyst surface, the addition is syn. There are no rearrangements and no regioselectivity issues. Every single alkene just reduces to the corresponding alkane. So hydrogenation is not regiospecific, there are no rearrangements, and it is stereospecific, syn addition. In closing, when you see an alkene, you should immediately think of the pi bond as electron rich, and therefore nucleophilic. When you see HBr or H2O in acid, you should ask yourself, where would the electrophile go and why? That naturally leads you to Markovnikov's rule and carbocation stability. When you see rearrangements, ask, could the carbocation be more stable if it shifted? That explains hydride and alkyl shifts. And when you see stereochemistry, either syn or anti-addition, ask what intermediate forms. Is it planar, like a carbocation, attacking from both sides, or locked, like a halonium ion or mercurinium ion, forcing anti? If you train yourself to always reason through the intermediates, stability, and stereochemistry, you don't have to use brute force memorization. Instead, your brain will build a framework, and that framework sticks with you long term because it connects logically. Till next time, crit.